Welcome to all of you at the Cosmology from Home conference. I want to start by expressing my gratitude to the organizers for inviting me and to all participants for being part of this exciting event. So enjoy the conference, and I hope to meet most of you during the discussion session. My name is Khaled. I am a research fellow at the University of Queensland. I spend most of my time either producing some results from current peculiar velocity surveys, such as DESI and Wally, or working on optimizing the design of future surveys, such as 4HS. And I'm so excited to show you today some of these efforts. Although this is not a DESI only talk, I'm using this picture of the 4-meter Mel telescope at Cape Peak, Arizona, which is currently hosting the amazing DESI survey. And I'm using this because it is the survey with the most eminent results. I would like to start by reviewing the state of cosmology. On this slide, I'm showing two images of the universe. On the left-hand side is an image of the universe when it was 400,000 years old after the Big Bang. And on the right-hand side is an image of the universe 13.8 billion years after the Big Bang. The image on the left-hand side shows the universe when it just started to be transparent. Before that, we cannot image the universe because it was filled with free electrons that made it opaque. It is an image of the fluctuation in temperature. The different colors correspond to different temperature, and the hotter temperature correspond to more matter today. And if you look carefully, you will notice that the scale in this image is in microkelvin, or 1 Kelvin divided by a million. That's a very small number. That means the universe was very close to uniform in temperature when it was just a few 100,000 years old, except for a tiny variation, which is 1 part in 100,000. The image on the right-hand side shows the universe today. It contains all kinds of structures, from planets to stars, to the Milky Way at the center here, to other galaxies, to clusters of galaxies. So matter tends to aggregate and form structures instead of just distribute itself uniformly. That is one of the most interesting questions in cosmology, how all these structures on the right-hand side came into existence from this very uniform temperature on the left-hand side. And the most accepted view is that the tiny variation in temperature on the left-hand side, which is 1 part in 100,000, grow by gravity into the structures that we see today. In summary, we can observe the universe when it was only 400,000 years old, and we can observe it today. And we know the laws of gravity that govern the universe in between. So basically, using any one of these two images to derive the cosmological parameters that describe the universe should lead to the same answer. Unfortunately, that is not the case. In fact, there are a few tensions between measurements from the early and late universe. For example, there is a tension between the measurement of the present-day expansion rate of the universe, H0, from the early universe, such as BO and CMB, and from late universe, such as surface brightness fluctuation, tip of red giant branch, and Tully-Fisher relation, and also Cepheid variables. And that's the plot on the left-hand side. On the right-hand side, there is another tension between early and late universe measurements. And this comes from measurements of the total matter density and the lumpiness of matter in the universe. It's called S8. which is a normalization, a kind of normalization of sigma 8. Also, the magnitude and the direction of our own galaxy motion in the universe and those of our galactic neighbors directly derived from late universe do not agree with the values derived from the early universe. So it seems that either the late universe or the early universe measurements are biased, or that we need to think about a new theory of gravity. And because our local universe affects all the light we see from distant objects, it's crucial to map the distribution of the total matter density. And here I'm talking about both luminous and dark matter. In the local universe, of course, to study, if we want to study precision cosmology. But we all know that galaxies are biased tracers, as they trace only the luminous matter. On the other hand, galaxy peculiar velocities, or the departure from the smooth expansion of the universe, are due to gravitational attraction of growing clustering of total matter. And because it arises as a result of gravity, peculiar velocities, unlike galaxy, offer measures of the total mass that is gravitationally driving them. I hope this has convinced you already, like all of you, hopefully, of the importance of peculiar velocity, especially in the local universe. With that all said, how do we actually measure peculiar velocities? I'm showing this simple equation which shows that the observed redshift z of any galaxy can be divided into two components. Z bar, which is a cosmological redshift corresponding to true distance, and it's always away from us because of the expansion of the universe. And Zp, which is a peculiar velocity or peculiar redshift. So you can think about peculiar velocity as a departure of a galaxy velocity from the mean value set by Hubble's law. In practice, to differentiate between both components, Z bar and Zp, we need to use something called distance indicator. We have two types of distance indicators. Primary distance indicator like Cepheid variables, which does not require any calibration from any other method. And secondary distance indicator like type 1e supernovae, Tully-Fisher relation, and fundamental plane relation. But those relations should be calibrated by the distance scale based on a primary distance indicator. Although Cepheid variable stars gave the most accurate measurements of distances, they become very faint beyond, say, 20 megaparsecs. And secondary distance indicator have to be used at beyond that distance. Type 1a supernovae is one of the very promising distance indicators in the era of the LSST. But until then, currently the largest peculiar velocity surveys such as DESI, Wally, and 4JAS are all using the secondary distance indicators, Tully-Fisher for spirals, and fundamental plane for ellipticals as their workhorses. Here's an example of how the Tully-Fisher relation is used to measure distances. Two sets of data contribute to the Tully-Fisher relation: photometric data, which provides a measurement of the distance-dependent luminosity of any galaxy, and spectroscopic data, which provide a proxy of for the distance-independent rotation speed of the galaxy. In order to use the Tully-Fisher relation to measure galaxy distances, a template relation is required. This template relation is derived from a sample of galaxies with known distances or a sample of cluster galaxies, and provides the calibrated relations between the absolute magnitude and rotation. Once we have this relation, the absolute brightness of a galaxy with known distance with unknown distance, can be read off from the Tully-Fisher template, given a measurement of its rotation. This can be used with galaxy apparent magnitude brightness to determine or to measure the distance via distance models. Okay, now we measured peculiar velocities of galaxies. What do we actually do with them? Now we will do some cosmology, and it turns out that we can do quite a lot of things. The first example that I'm showing here is cosmic cartography. And cosmic cartography studies are interested actually in their own right. In the same way that many people historically are interested in mapping the Earth, there are like some people who are extremely interested in mapping our place in the universe. But in addition to this, these maps are useful for other studies. For example, here is the distribution of about 16,000 elliptical galaxies from 6DF survey plotted in red and SDSS survey plotted in blue. And these BV samples are color coded by the redshift, so the darker colors means higher redshift. And this is shown in an height-off projection, or in a galactic longitude and latitude. What we are interested in this plot is the direction of the external bulk flow, which is a bulk flow due to some structures outside of our redshift survey. So these are structures that we don't see. And this is shown as a red star for 6DF sample and as blue circle for SDSS. As you see, it agrees with previous measurements, and it happened to be just in between the position of the two most prominent super clusters in the nearby universe, such as the black triangle is a Vela supercluster, and Shapley supercluster is plotted here as a square. So this is maybe an indication of some bigger structure hidden behind our own galaxy. Or maybe these two structures are connected somehow. The second example of useful usage of peculiar velocities is to measure the growth rate of structure and test different theories of gravity at low redshifts. And the measurement of growth rate of structure at low redshift is almost exclusive to peculiar velocities. I'm talking about redshift below 0.1 here. So here we constrain the growth rate of structure by comparing observed fundamental plane or directly measured fundamental plane peculiar velocities for 16,000 galaxies from 6DF survey and SDSS survey. We compare these with predicted velocities from redshift surveys using linear theory. The plot to the right shows constraints on the growth rate of structure using different galaxy surveys at various effective redshift, and this is plotted in as gray points. And the red data point is a constraint from 6DF plus SDSS peculiar velocities. And this growth rate f can be parameterized as a function of omega m and the growth index gamma, which is determined by the theory of gravity. For the standard lambda CDM cosmology with, say, flat geometry, cosmological constant, and cold dark matter, gamma should be around 0.55. While for alternative theories of gravity, like DGB for example, gamma takes on other values. So after trying several variations of cosmological parameters to find the best fit for our value, we came to the very cautious conclusion that our results favor values of the growth rate of the growth index gamma higher than 0.55, or a Hubble constant h naught higher than 70 km per second per megaparsec, or a fluctuation amplitude sigma 8 less than 0.8, or some combination of this. Again, we were very cautious here because I know this is like very difficult to put like a conclusion on this kind of tensions at the moment. BQM velocities are also important for correcting h naught measurements from supernovae, for example, and gravitational waves. In particular, last year, working with the Pantheon team, we published a series of papers to improve on the original Pantheon catalog by using an improved BQM velocity model. And in this model, we calculate the local motion, but in redshift space. And we also account for the external bulk flow. And like doing all this in redshift space actually makes everything less dependent on cosmology. Hopefully by now I have convinced you all that BQM velocities are important and we should go ahead with some future plans. So now I will show you how we are planning to expand on these studies in the future. One of these surveys is DESI, which has started already. And DESI stands for the Dark Energy Spectroscopic Instrument. And DESI is actually conducted on the male 4-meter telescope at Kitt Peak National Observatory near Tucson, Arizona. So after the light passes the lenses, it will reach fiber optics cables in the focal plane at the top of the telescope. And we have 5,000 of these fibers, and they are controlled by little robotic positioners, which takes under 5 minutes to reconfigure. And to put this in comparison, the AT, for example, at Siding Spring here in Australia, have 300 fibers, which takes about 45 minutes to reconfigure. So like DESI is like already like a few steps ahead in this technology. Then these optical fibers sense light down to 10 spectrographs, which will allow us to measure redshift and many more parameters for each galaxy, such as the velocity dispersion of stars inside each galaxy, and that will help us to establish the fundamental plane relation. Or we can also measure the rotation of each galaxy to establish the Tully-Fisher relation, which are the two workhorses for the peculiar velocity survey. The redshift range will be from 0 to 3 in units of the speed of light over 14,000 square degree. And one of the main goals of DESI, as you see here, is to measure growth rate of structure with redshift space distortion, or RSD. In the coming slides, I will show you how, by adding only a few thousand directly measured BQM velocities, we can improve on this goal. So what are we going to observe? Basically, when the moon is up, DESI will conduct a magnitude limited bright galaxy survey, and that will be of approximately 10 million galaxies with a median redshift of 0.2. Otherwise, and by otherwise I mean like when it's dark, when there is no moon, DESI will measure luminous red galaxies up to redshift of 1. To go to even higher redshift, DESI will target bright emission line galaxies up to redshift of 1.7, and quasars will be targeted both as direct tracer of the underlying dark matter distribution and at higher redshift, so between 2 and 3.5 for the Lyman alpha forced absorption feature in their spectrum. So, which will be used to trace the distribution of neutral hydrogen. So, in total, more than 30 million galaxy and quasar redshifts will be obtained to measure the BO feature and determine the matter power spectrum, that including redshift space distortion. If you look at this will be an order of magnitude higher than all the current, all the previous redshift surveys combined. So if you take all the previous redshifts, combine them together, multiply by 10, that will still be less than what DESI will get. Just a summary of what DESI peculiar velocity is. So this is a secondary target program that will hopefully become the largest collection of distance measurements to a nearby galaxy ever assembled, and that will enable a whole range of science. We already have some results from science verification. For example, we submitted the target selection paper early this year, and you can find it on arXiv already. And within a month, 2 more papers should appear on arXiv also. One that contains all details about Tully-Fisher relation, such as how we measure rotation using several DESI fibers, and the relation itself, like how the relation itself is established. Khaled is leading this paper, and the second SV paper will be all about fundamental plane, how we measure velocity dispersion, and we'll also have several comparisons with previous surveys. So the plot on the left here shows the photometric redshift distribution of our DESI BV survey. The black solid and dashed and dotted lines correspond to full and Tully-Fisher and fundamental plane DESI sampled respectively. The green, red, and blue lines are distribution of current or like other available surveys such as Cosmology 4, Tully-Fisher, or 6DF fundamental plane, and also STSS fundamental plane survey. On the right hand side, I'm showing here forecast for constraints of the growth rate in redshift bins from the DESI BGS. This is plotted as black points, and as peculiar velocities as blue point, and combined red, like the combination of both of them as red points. And the bottom panel actually shows, the bottom panel on the right hand side shows the relative error on the growth rate in each of these redshift bands. The combined constraints are substantially improved with the inclusion of the peculiar velocity survey compared to only BGS using RSD alone. So this will allow for much larger distinction between different parameterization of gravity at low redshift. Okay, so DESI will be great, but it covers only the northern hemisphere. So we proposed another survey in the north. We proposed this, the foremost hemispheric survey, or 4GS for short, in the south, which was already accepted and will start sometime in 2024. So basically, this is a spectroscopic redshift survey of about 6 million galaxies, covering 16,000 square degree, all of the southern sky, basically, except for the zone of avoidance. So the immediate science goal for 4GS will be to map the density and velocity fields and measure the growth rate of structure. And to put 4GS in context of wide field survey. This figure shows other surveys like the ASCAP Wallaby survey, LSST, Vera Robin LST, and Euclid. The points shows our preliminary input catalog. So the main survey is shown in black, BQI velocity is in red, and you can see how it will enable us actually to dive deep and to narrow the zone of avoidance for some of the BQI velocity signs. Okay, and here's some forecasts but this time is for the growth rate of structure as a function of redshift again, but this time is for 4HS. And we're combining it again with DESI BGS, just like to compare between 4HS and DESI BQI velocities, but you can like combine everything and combine BQI velocity from 4HS with BQI velocity from DESI. But here I'm showing just for BQI velocity from 4HS and combine them with DESI BGS. So again, the top panel is a comparison of the expected measurement from 4HS alone and in combination with DESI BGS compared to the prediction, and we're comparing this with the prediction from Planck, which is the bands as you see. And the bottom panel shows the percentage error of the growth rate in each band of 4HS, DESI BGS, and their combination. You can see the improvement again is significant by adding some BQI velocities, especially at low redshift where BQI velocity have the more constraining power than any other method. Okay, now just to summarize where we are and where we are going with BQI velocity surveys. So until very recently, and here I'm talking about until 2022, the largest homogeneous sample of directly measured BQI velocities was the 6 degree field galaxy survey, or 6DF. And that was around like 8,000 galaxies. This survey covered most of the southern hemisphere up to redshift of about 0.06, which is about like 180 megaparsec per little h. And in this survey, they used, I wasn't involved in this survey, and this is the only survey that I'm showing this table that I wasn't involved in. And in this survey, they used the fundamental plane relation, and their final catalog of BQI velocity was published by Chris Springop and others in 2024. However, that catalog has been refined and used many times by different groups to measure, for example, the growth rate of structure, F sigma 8. But the other groups also used it to measure the bulk flow and many other cosmological parameters. What you can see on the right-hand side is the projection of the survey in supergalactic plane SGX, SGY, at a slice of SGZ of 0. And you can see it covers most of the southern sky except for the zone of avoidance part, and that was up to, again, 180 megaparsec per little h. So then in 2022, Colin Howlett, myself, and others, we published a new catalog of true distances and BQI velocities of about 34,000 early type galaxies. And we also used fundamental plane relation and data from SDSS. And you can see like the increase in numbers between like 8,000 for 6DF and 34,000 like from SDSS. And this homogeneous sample is currently the largest set of BQI velocity produced to data. And that extend to the reach of BQI velocity survey up to a redshift of 0.1. And this is actually can translate into about like 300 megaparsec per little h in this beautiful supergalactic plane projection. So we improved on the redshift, and that translates into a larger number of peak velocities, and we covered a different area of the sky. So a 60F was covering only the south, tried to cover the north, and we also extended the redshift. But there is still a lot of skies, as you can see, there is a lot of sky that is not covered by anything. So early this year, Helen Courtois, myself, and others published the first results from a new survey called Wally. And our results were coming from the pilot survey of Wally, which has been conducted using the Australian SKA or the ASCAP. We drive it Tully Fisher distances using the Willoughby 21 centimeter velocity wedges and infrared wise W1 magnitudes. So although the Willoughby survey will extend only to redshift of 0.07, similar to 60F survey, and will also cover almost the same area as 60F. You can see that clearly in the supergalactic plane projection. It will be using spiral galaxies instead of elliptical galaxies, and that will be in completely different wavelengths. So the 60F was in optical, and this one optical spectroscopy, and this one is 21 centimeter. So that will be great actually to test things like galaxy biases in different wavelengths, and because radio wavelengths can penetrate into dust, it will be great to observe deep into the zone of avoidance. So it's not a waste of time. Of course, it's like it will be an assuring for us that like fundamental plane and Tully Fisher, they both work, and like spiral galaxies, we can compare it with elliptical galaxies, because spiral galaxies are usually like, you usually think of spiral galaxy are like star forming galaxy, and you can think about elliptical galaxy as like old and dead red stars all about. So Willoughby will be great in that sense. So our pilot survey actually suggests that we'll get about 200,000 Tully Fisher distances, and that would be the result of the full Willoughby survey. This is much higher than what was expected in the initial proposal. And this number may be slightly optimistic, given that we only observe nearby structures during pilot survey. So maybe we'll get half of this, but even if we get half of that, or even if we get like only 25% out of this, that will be 50,000 Tully Fisher distances. That's 5 times larger than all the current Tully Fisher distances combined. Okay, so now with DESI. So DESI peak velocity survey is the first ever peak velocity survey, to my knowledge, to use both fundamental plane of elliptical galaxies and Tully Fisher of spiral galaxy on the same instrument. So basically everything in this survey is just amazing. So overall, we predict that the final DESI peak velocity survey will obtain about 133,000 fundamental plane distance and peak velocities, and about 35,000 Tully Fisher based peak velocity measurements. And that will be over an area of 14,000 square degree. The survey will extend to up to 450 megaparsec per little h, as you can see in this projection, which will be unprecedented. So our target selection paper is currently under review and is already on archive. 2 other papers should be on archive in about a month from now, one on Tully Fisher and one on fundamental plane. So keep an eye out for these papers. And that's the last survey over a 5-year campaign starting in 2024. 4HS will measure optical spectra and redshifts for about 6 million galaxies over the whole southern sky, and that will be at low redshifts, of course, and they will include some distance and peak velocity. And when I'm saying some, we're talking here about like 450,000, and this is close to 500,000 galaxies in the nearby universe. And like if you compare it, like I'm talking just before 2022, the largest sample was 8,000, and in 5 years from now we'll have 500,000. That's amazing. So 4HS will be using only fundamental plane over the whole southern sky, and it will push deep again into the zone of avoidance. It will go like farther than any previous survey except for DESI. They will cover almost the same redshift as DESI. So over the next 5 years, combining DESI and 4HS, we are hoping to produce the first ever 1% measurement of the growth rate. So maybe then we'll be able to tell you all if our theory of gravity is a correct one or not, or do we need to look for alternative theories, and we might also solve like some other tensions. I'm not saying peak velocity will solve all the tensions, but I'm saying we might be able to give you some certainty here. With that, I would like to thank all of you once again for your time. I hope to see as many of you as possible during the discussion session to chat about these surveys and maybe answer some of your questions. So see you all. Bye.